In this video we shall see the remaining problems for the bar elements and truss elements. So the next problem number 8, we are supposed to determine the nodal displacement and stress in each element and reaction at the fixed support for the thin plate of uniform thickness of 1 mm as shown in the figure 7.8 below. Consider Young's modulus as 200 gigapascals. Density of the plate has 76.6 into 10 power minus 6 Newton per millimeter cube. In addition to its weight, it is subjected to a point load of 1 kilonewton at its midpoint. So 100 newtons is acting exactly at the center. Model the plate with the two bar elements. So clearly in the question itself, they have told that we have to consider two elements. So 3 nodes. So let us consider the FE model. Let us start with the solution. So FE model, so modeling the given bar has two elements having two nodes each. It is written here. So left hand side it is fixed, 60 mm is the length. So cross sectional area I can consider with the 60 mm and A2 with 30 mm. There is 100 newtons acting exactly at the node 2. So element 1 and element 2 has been written. Element 1 is 120 mm in length, element 2 is also 120 mm in length. Here we have considered the element 1 and element 2. So you can see the figure on the left hand side, figure 7.8. There are three markings of triangle ABC and CDE. So triangle A, B and C, we know that tan theta is opposite by adjacent, that is AB divided by AC. So AB is nothing but 15 because 30 plus 15 plus 15 is equal to 60. So AB is equal to 15. AC is nothing but 240 mm, directly the value is given. So AB by AC is 15 by 240. So approximately the theta value will be 3.57 degrees. So we have found the value of theta. Now coming to the smaller triangle, that is C, D and E. We know that theta is 3.57 at C. Similarly, CD is 120 mm. We have to calculate the value of DE. So DE, let us consider the value to be x. So tan theta is equal to DE or x divided by CD, that is 120. So x by 120 is equal to tan of 3.57. So directly x value we will get has 7.5 millimeters. So at the point D, I can consider the radius has 60 minus 7.5 minus 7.5, that is 45 mm. So the same concept of similar triangles is used here, and we have tried to calculate the area of element 1 and element 2. So volume should be same, area into thickness should be same, hence area is 120 by 2 into 60 plus 45 into 1 is equal to the area of the second element. So which comes to 52.5 millimeter square, and similarly for the second element also it comes to 37.5 millimeter square. Area 2 comes to be 37.5 millimeter square after the modification. So now we have the values of E1, E2, A1, A2, L1, L2. We have the value of F2. We have a rho 76.6 into 10 power minus 6 Newton per millimeter square cube. Thickness 1 millimeter. So calculating the stiffness matrix, K is equal to A by L. So direct substitution of the various values, we get K1 is equal to 10 power 5 into 0.875 minus 0.875 minus 0.875 plus 0.875. Similarly, K2 0.625 minus 0.625 minus 0.625 and plus 0.625. So adding K1 and K2, we will get the global stiffness matrix. F is equal to A into L into F divided by 2 into 1 and 1, where F is nothing but the weight density, which is equal to rho. So it is 37.5 into 120 into 76.6 into 10 power minus 6 divided by 2 is the value of F2. Similarly, F1 also we will get in same lines. So F1 value is 0.241 and F2 value is 0.1723. So adding the global stiffness matrix, arriving at the value of Q and arriving at the value of F, we get the equilibrium condition K into Q is equal to F. Substituting the value of K, substituting the value of F, we get the equation as K into Q is equal to F as 10 power 5 into 0.875 minus 0.8750 minus 0.875 15 minus 0.625 0 minus 0.625 plus 0.625. Okay, for column to row 2 it is 1.5. The value is 1.5 because we are adding 0.875 with the 0.625, so it comes to 1.5. So we know that Q1 is equal to 0. When we are applying the boundary conditions, we know that Q1 is equal to 0. So by elimination method of handling the boundary condition and eliminating the corresponding row and column with respect to Q1, we can eliminate the first row, first column. So only second row, second column and third row, third column remains. So 1.5 minus 0.625 minus 0.625, 0.625 into Q2 Q3 is equal to 100.41 and 0.1723. So solving for this, solving for Q2 and Q3, two unknowns, two equations. So directly we can substitute and solve it. So Q2 value we will get as 1.15 into 10 power minus 3 mm. Q3 has 1.152 into 10 power minus 3 millimeters. So this is the nodal displacement vector. Next, to calculate the stress, so sigma is equal to E into 1 by L E into minus 1 into Q1 Q2. So directly sigma 1 we will get. Substituting the values and calculating, we get sigma 1 has 1.915 Newton per millimeter square, tensile in nature. Sigma 2 has 0.005 Newton per millimeter square, that is compressive in nature. Sign is negative because it is compressive in nature. So both sigma 1 and sigma 2 value we will get. So we shall see a truss problem now. So this is the problem definition. Consider a 4-bar truss shown in figure. It is given that E is 2 into 10 power 5 Newton per millimeter square and A is 100 millimeter square for all the elements. Determine the element stiffness matrix for each element. Assemble the elemental stiffness matrix for entire truss. Using the elimination approach, solve for the nodal displacement, calculate stress in each element, calculate reaction forces. So the problem is given. We have 1, 2, 3 and 4 trusses and 3 supports. There is a load of 25,000 newtons acting at node 3 for truss 4 and truss 3 and truss 2 join at node 3. So at node 3 there is a load of 25,000 newtons. Node 1 and node 4 are completely fixed. Node 2 is free to move in the horizontal direction. So the dimensions are also given. The distance between node 1 and node 4 is 30 mm. Distance between node 1 and node 2 is 40 mm. Distance between node 2 and node 3 is again 30 mm. So the length of node 1, node 2 and node 4 is directly deduced from the figure itself, whereas node 3 the value can be obtained by applying the Pythagoras theorem, wherein it is equal to 40 square plus square root of 40 square plus 30 square. So the length of node 3 will be square root of 40 square plus 30 square. So writing down the nodal coordinate data. So for node 1, writing the table for node number 1, 2, 3, 4, x coordinate for node 1 is 0, y coordinate is 0, x coordinate for node 2 is plus 40 and y coordinate is 0, x coordinate for node 3 is plus 40 and y coordinate is plus 30. Similarly for node 4, x coordinate is 0, y coordinate is plus 30. So if we are seeing the element connectivity, then element 1, 2, 3 and 4 are there, and initial nodes we are having node 1, 2, 3. So element 1, the first node is at, for element 1 initial node is 1, final node is 2. For element 2 the initial node is 2, the final node is 3. For element 3 the initial node is 3, final node is 1, and for element 4 the initial node is 3 and final node is 4. So length of the element directly for element 1 30, element 2 30, element 1 it is 40, element 2 it is 30, element 3 it is square root of 40 square plus 30 square, which is nothing but 50. For element 4 it is again 40. So direction cosines L and M. So L is nothing but cos theta and M is nothing but sin theta. So writing down the direction cosines, we get 1 0 0 1 minus 0.8 and minus 0.6 minus 1 and 0. So for element 1, L is nothing but 40 minus 0 by 40, that is equal to 1. M is nothing but 0 minus 0 by 40, that is equal to 0. Similarly, for all the elements, we are supposed to calculate the values of L and M. So the elemental stiffness matrix is obtained from the formula for the truss element, that is AE by L into L square ML minus L square minus ML, ML M square minus ML minus M square, L square minus ML L square ML minus ML minus M square ML M square. So the stiffness matrix K can be written for element 1 has 10 power 5 into 5 0 minus 5 0 0 0 0 0 minus 5 0 5 0 0 0 0 and 0. Similarly, we are supposed to calculate the stiffness matrix for element 2, element 3 and element 4. So direct substitution and calculation of the values. It is simple. Simply direct substitution and calculation of the values. So the next step, we are supposed to add the global stiffness. We are supposed to add the elemental stiffness matrix to get the global stiffness matrix. So we have to add K1, K2, K3 and K4. So here it is very necessary to write the node numbers. So for K1 we have the global degrees of freedom has 1, 2, 3 and 4. For K2 we have 3, 4, 5, 6. For K3 we have 5, 6, 1 and 2 again. For K4 we have 5, 6, 7 and 8. So wherever 1 is coinciding with 1, it has to be added. So if we are observing carefully, K1 we have 1 coinciding with 1, which is equal to 5. Similarly in K3 also we have 1 coinciding with 1, that is 2.56. Hence while arriving at the global stiffness matrix we have to add 5 and 2.56. So wherever the common terms are there, they are required to be added in order to get the global stiffness matrix. So next is global displacement vector, which is Q1, Q2, Q3, Q4, Q5, Q6, Q7 and Q8, and global force vector F1, F2, F3, F4, F5, F6, F7 and F8. We know that F3 is 20,000 and F6 is minus 25,000. So directly K into Q is equal to F. K into Q is equal to F. Substituting the values for K into Q equal to F. I'll move to the next slide wherein we have equated both the equations. So here K into Q is equal to F has been represented. So from elimination method of handling the boundary condition from figure 1, we know that Q1 and Q2 is equal to 0 because node 1 is hinged. Q4 is also equal to 0 at node 2 because it is a roller support. Q3 is 0. Q8 is also 0 because node 4 is also hinged. So Q1, Q2, Q7, Q8 are 0. At Q4 it is 0 because it is a roller support. So only the values of Q3 is available and Q6 is available. All others will be removed. That is first row first column, second row second column, fourth row fourth column, seventh row seventh column and eighth row eighth column will be removed. Only 3, 5 and 6 will remain. So Q3, Q5 and Q6 alone will remain. So the entire matrix will be reduced to 3 into 3 matrix. So we can rewrite it as 5, 0, 0, 0, 7.56, 1.92, 0, 1.92, 8.1 into Q3, Q5, Q6 into 10 power 5 is equal to 20,000 0 minus 25,000. So 3 unknowns, 3 equations. Solving we get the value for Q3, Q5 and Q6. So Q6 is minus 32.84 into 10 power minus 3 millimeters. Q5 is 8.34 into 10 power minus 3 millimeters and Q3 is 0.04 millimeters. So substituting the values in the displacement matrix, we get 0, 0, 40 into 10 power minus 3, 0, 8.34 into 10 power minus 3, comma minus 32.84 into 10 power minus 3, comma 0 and 0. So for calculating the stress, we know that sigma is equal to two into 10 power 5. Sigma is nothing but E divided by L into minus L minus M L M into Q1, Q2, Q3 and Q4 for element 1. So for element 1 it is 2 into 10 power 5 by 40 into minus 1 0 1 0 into 0 0 40 into 10 power minus 3 0 into Q1, Q2, Q3, Q4. So I will get the value of sigma 1 to be 200 Newton per millimeter square. Similarly, sigma 2 is 2 minus 218 into 10 minus 218.93 Newton per millimeter square. Similarly, solving for sigma 3 and sigma 4 for element 3 and element 4. We will move to the next slide. So sigma 3 is nothing but 2 into 10 power 5 divided by 50 into 0.8, 0.6 minus 0.8 minus 0.6 into 0.00834 minus 0.0324, 0 and 0. So sigma 3 is minus 52.112 Newton per millimeter square. Similarly, sigma 4 we will get as 41.7 Newton per millimeter square. So the total reaction forces can be obtained from the equation R is equal to K into Q minus F. So here only those rows of K corresponding to support degrees of freedom are required, and F is equal to 0 for these degrees of freedom. Hence we can solve this equation and directly get the values for R. So R we will be getting as reaction forces we will get as minus 1582.76, R2 is 3127, R3 is 0, R4 26640, R5 is 0, R6 is 0, R7 is minus 4170, R8 is again 0. So from the diagram we can write down the reaction forces wherever they are acting. R1 will be acting, R2, R3 is 0, R4 will be acting, R7 and 8 will be acting, 5 and 6 are 0. So next problem, 2 bar stress element is shown in the figure. Determine the nodal displacement, stress in each element and reaction at the supports. Take E is equal to 2 into 10 power 5 Newton per millimeter square. A is equal to 200 millimeter square. So the diagram is given. There are two nodes, there are two trusses, truss 1 and truss 2, and 3 nodes. So node 1, x is 900, y is 0. For node 2, x is 500, y is 300. For node 3, x is 0, y is 300. So element connectivity data. For element 1, initial node is 1, final node is 2. For element 2, initial node is 2, final node is 3. Length of the element is, for node 1 it is square root of 300 square plus 400 square, that is 500 millimeters. For element 2 also it is 500 millimeters. Directly we can see from the diagram. Direction cosines L and M. For element 1 we have to write down the direction cosines. So L is minus 0.8, M is 0.6 for element 1, and for element 2 L is minus 1 and M is 0. So next, formula of the stiffness matrix, it is nothing but AE divided by L into L square ml minus L square minus ml, ml m square minus ml minus m square, minus L square m minus ml L square ml minus ml minus m square ml m square. So K1 value we will get, similarly K2 also we will get. For K1 we can observe that we have 1, 2, 3 and 4, that are the degrees of freedom, that is global degrees of freedom, and for element 2 we have 3, 4, 5 and 6. Hence for obtaining the global stiffness matrix while adding K1 and K2 we have to take care of the common terms, that is node 3 and node 4, which are there in both the element 1 and element 2. The degrees of freedom for node 3 and 4 are there in both node both element 1 and element 2. Since node 2 is common, the degrees of freedom associated with node 2, that is 3 and 4, will be present in both element 1 and element 2. So combined global stiffness matrix has to be written down. So here you can clearly see how the element 3, 4 has been combined together to get the global stiffness matrix. Next, once the global stiffness matrix is generated, global displacement vector, that is Q1, Q2, Q3, Q4, Q5 and Q6, and global force vector F1, F2, F3, F4, F5 and F6. So we are clearly aware from the question itself that F1, F2, F3 is 0, F4 is minus 12 into 10 power minus 3, F5 is 0, F6 is 0. So equilibrium equation K into Q is equal to F. So substituting the value of K, Q and F in the equilibrium equation and writing it down, we get the combined equation in the next slide. So here you can see the combined equation. Now applying the boundary conditions wherein Q1, Q2, Q5 and Q6 is equal to 0, and using the elimination method of handling the boundary condition and eliminating the corresponding rows and columns, the matrix reduces to 2 into 2 matrix. So Q1, Q2, Q5 and Q6 are equal to 0. Hence row 1, column 1, row 2, column 2, row 5, column 5, row 6, column 6 can be eliminated, and we will get a 2 into 2 matrix. So Q3 and Q4 are the two unknowns and two equations are there. Solving for this, we can get the value of Q3 and Q4. So the Q3 value is Q3 value will be minus 0.2 mm and Q4 value is minus 0.683 millimeters. So next, calculating the value of sigma or the stress. It is nothing but E by L into minus L minus M, L into M into Q1, Q2, Q3, Q4. So sigma 1 value will be minus 99.92 Newton per millimeter square. That is the stress in the equation, stress in element 1. Similarly, stress in element 2 can be calculated by the same formula, and we will get sigma to be minus 80 Newton per millimeter square. Now the reactions at the support has to be calculated. So for that we can find out the reaction at the support from the equation R is equal to K into Q minus F. So using only those rows of K corresponding to supports are required, and F is equal to 0 at those support for the given problem. Hence R1, R2, R5 and R6 is equal to 10 power 5 into corresponding K values for R1, that is row 1, column 1, row 5 and column 5, row 1, row 2, column 1, column 2, row 5, column 5, row 6, column 6 are to be utilized. And solving, we get the values of R1, R2, R3, R4, R5 and R6 has a minus 15987.2 newtons, minus 11990 newtons, R3 equivalent to 0, R4 equivalent to 0, R5 16,000 newtons, R6 equivalent to 0. So next, moving on, we have to write the elemental connecting data for this particular problem. So the table for elemental connecting data also has been written down. So we have two elements, element 1 and 2. So the element 1 is at node 1, so initial node is 1, final node is 2. For element 2, initial node is 2 and final node is 3. So the length of the element 1 is nothing but square root of 750 square plus 500 mm square, so which comes to 901.387. and the length of element 2 directly from the figure, it is deduced to be 750 millimeters, hence 750 we have written. Now the direction cosines L and M are to be calculated. So L is equal to x final node minus x initial node divided by LE, and M is equal to y final node minus y initial node by LE. So calculating the value of x and x initial from the formula given, we will get the values of L to be 0.832 and 0.554 for element 1, and for element 2 it is going to be minus 1 and 0, minus 1 and 0. So once we complete the nodal coordinate data and the elemental coordinate data, we will move to the next step in the next slide. Moving on to the next problem, here we will see we have two bat truss shown in figure. Determine the nodal displacements and the stress in each member. So we are supposed to calculate the displacement as well as the stress in each member. Find the support reaction above and take E is equal to 200 gigapascals. So the reaction is we have to calculate the reactions at the support. As seen from the figure, we have two elements and 3 nodes, and there is a load of 50 kilonewton that is acting at node 2, where element 1 and element 2 are meeting each other. And we also have the data given. So E is 200 gigapascals. So let us move on and draw the finite element model of this particular problem. So the problem statement and the figure are only the data that has been given. So after that we are supposed to draw the finite element model in order to solve this problem. So moving on, finite element model of this particular problem we have drawn on the right hand side of this slide. We can see FE model which has been drawn on the right hand side. There is a 750 mm width and 500 mm height, and 1200 mm is the length of the element 1 which is given. 1200 mm square, that is the area of the element, it has been given. 1000 millimeter square is the area of cross sectional area of the second element, and this also data has been given, and there is a load of 50 kilonewton acting at node number 2. This data also has been given. So we can calculate the length of the element 1 by applying the Pythagoras theorem, which is equal to square root of 750 square plus 500 square. So next, writing down the nodal coordinate data. So we have node 1, node 2 and node 3. So the x coordinate of node 1 will be 0 and 0. For node 2, the x coordinate is 750 mm and the y coordinate is 500 mm. For node 3, the x coordinate is 0 and y coordinate is 500 mm. So the nodal coordinates also has been written down. So in this slide, the next step, writing down the element stiffness matrix. So the element stiffness matrix for the truss element we have derived. In the previous video it is clearly evident, the derivation, and the final formula is KE, that is the element stiffness matrix for the truss element, is equal to A suffix E into capital E suffix small e divided by L suffix E into L square ml minus L square minus ml, ml m square minus ml minus m square, minus L square minus ml L square ml, minus ml minus m square ml m square. So this is the matrix of the stiffness, and we have derived this in the previous video. If you are having any doubts, you can refer the previous video. So this formula you are supposed to remember. For the truss element, the formula for the elemental stiffness matrix you are supposed to remember. So substituting the value for element 1, the value of A will be that of the element 1, which is equal to 1200 millimeter square. Similarly, E value is 200 gigapascals, so 2 into 10 power 5, and L value we have calculated, which comes to 901.387. so substituting these values, and values of L and M we have written down in the element connecting data. So writing down the values of L square ml wherever applicable in the stiffness matrix, and deducing the stiffness matrix for element 1. Similarly, deducing the stiffness matrix for element 2. So once both the stiffness matrices are deduced, then the next step is to add the element 1 and element 2 stiffness matrix. So if we observe carefully, the common node is node number 2. The common node is node number 2. So if you see the first element, 3 and 4 will be added to the 3 and 4 of the second stiffness matrix. You can observe here 1, 2, 3 and 4 are the 4 variables that are present in the first elemental stiffness matrix. Similarly, 3, 4, 5, 6 are the 4 variables that is present in the second stiffness matrix, and 3 and 4 correspond to the node number 2. The row 3, column 3, row 4, column 4 correspond to the node number 2. So node number 2 is common in both the elemental stiffness matrices. In elemental stiffness matrix for element 1, node number 2 is there, and it is represented by the row 3 and column 3, row 4 and column 4. Similarly, in elemental stiffness matrix 2 also we have we have second node number 2, which is represented by the row 3, column 3 and row 4, column 4. So taking these common terms and adding up to get the global stiffness matrix. So K is equal to K1 plus K2. So the global stiffness matrix is written down in the slide. So next, displacement vector. So there are 6 variables, hence 6 displacement vectors will be there: Q1, Q2, Q3, Q4, Q5 and Q6. So if we observe carefully, Q1 and Q2 correspond to node number 1. It is the displacement in x axis and y axis. Q3 and Q4 correspond to node number 2. It is the displacement in x-axis and y-axis for node number 2. Similarly, Q5 and Q6 represent node number 3. It is the displacement of the node number 3 in x-axis and y-axis represented by Q5 and Q6. Similarly, global force vectors, we have F1, F2, F3, F4, F5, F6. So F1 and F2 are the loads acting on node number 1 in x-axis and y-axis respectively. F2, F3 and F4 are the loads acting on node number 2 in x-axis and y-axis respectively. F5 and F6 are the loads acting on node number 3 in x-axis and y-axis respectively. So if we observe the diagram, clearly there is no load acting at node number 1, node number 3. Only at node number 2 we have a 50 kilonewton load acting in the downward direction, that is in the y direction. Hence only F4 will have a value of minus 50 kilonewtons. In the convention is minus because it is acting in the downward y direction. Hence we are representing it as minus 50. Rest all values of F will be 0 since there is no load acting at any other nodes. So the equilibrium equation comes to be K into Q is equal to F. So global stiffness matrix we have deduced the force vector, we have deduced the displacement vector. So now substituting this in the equilibrium equation. So now moving on, we know that Q1, Q2, Q5 and Q6 are 0. When we are applying the boundary condition, it is evident that Q1, Q2, Q5 and Q6 are 0 because node 1 and node 3 are completely fixed. They cannot move in x direction or in y direction. And only node 2 is free to move in either x or y direction. Hence displacement at x and y axis at node 1 and node 3 is equal to 0. Hence Q1, Q2, Q5 and Q6 become 0. So by elimination method of boundary conditions, eliminating row 1, column 1, row 2, column 2, row 5, column 5, row 6 and column 6, we get the matrix in a simplified form as a 2 by 2 matrix, which is written down in the slide as seen here. So now we have two unknowns Q3 and Q4 and two equations. So solving for Q3 and Q4, we get the value of Q3 as 0.279 millimeters and Q4 as minus 1.03 millimeters. So the nodal displacement vector for the entire structure can be written as Q is equal to 0, 0, 0.279, minus 1.03, 0, 0. So displacement vector is deduced. Now next is to calculate the stress in each element. So stress sigma 1 is given by E by L into minus M L M into Q1, Q2, Q3, Q4. So substituting the values and calculating, we get sigma 1 to be minus 75.32 Newton per millimeter square. So we have calculated the sigma in the stress in the first element. Similarly, for the stress in the second element, we have to calculate, which is seen in the next slide. So as clearly seen, the stress in the second element is given by sigma 2 is equal to E by L into minus L minus M L M into Q3, Q4, Q5, Q6. So substituting the values and solving it, we get the stress to be 74.64 Newton per millimeter square. 74.64 Newton per millimeter square. So sigma 1 and sigma 2 values we have calculated. Next step is to calculate the support reaction. So the reaction forces at the support is given by the formula R is equal to K into Q minus F. R is equal to K into Q minus F. So the reaction forces R1, R2, R3, R4, R5, R6 is equal to stiffness matrix K multiplied by the displacement Q minus the load F. So substituting the values and doing the matrix calculation, we get the values for the reaction forces. So R1 is found to be 324 newtons, R2 is found to be 49,907 newtons, R3 is equivalent to 0, R4 is also equivalent to 0, R5 is coming to be minus 74214 newtons, and R6 is coming to be 0 newtons. So with this we have solved the problem number 11. So one more type of problem we will see. So consider a 3-bar truss as shown in figure. It is given that E is equal to 2 into 10 power 5 megapascals. Determine the nodal displacement and stress in each member. Find the support reactions. So the figure is given to us. We have 3 elements and 3 nodes, and node 1 and node 2 are fixed. Node 1 is completely fixed. At node 2 we have x movement along the x-axis. So displacement in x-axis is allowed at node 2, whereas node 3 is completely free to move in both x-axis and y-axis. So calculating the length of the each of the elements. So we have 400 and 400, that is 800 millimeters is the length of element 1, and for element 2 we have to calculate the value by using the Pythagoras theorem, which is equal to square root of 400 mm square plus 400 mm square. Similarly for element 3 also we have to calculate the value using the same formula. So it comes to be 565.68 millimeters. The length of element 2 and element 3 comes to be 565.68 millimeters. We are simply applying the Pythagoras theorem and calculating the length of the hypotenuse. So it is simple mathematics. So next step, to write down the nodal coordinate data. So we have nodes 1, 2 and 3, and x-axis, x coordinate and y coordinate for node 1, 2 and 3 is written down. So node 1 is at the origin, hence 0 and 0. Node 2 is at a distance of 800 meters in x-axis and y-axis value is 0. Node 3 is at a distance of 400 meters, 400 mm in x-axis, and y also it is 400 mm. Hence the nodal coordinates for node 1, 2, 3 in both x and y axis is written down. Next, elemental connectivity data. So element 1, 2 and 3 is given. So the initial node is for the element 1 is 1, final node is 2. For element 2, initial node is 2, final node is 3. For element 3, the initial node is 1, final node is 3. So the length of element is 800, directly we can get from the figure. For node 2 and 3 we have calculated using the Pythagoras theorem. It is found to be 565.68 for both node 2 and 3. Next, direction cosines L and M. So for node element 1, L value is 1 and M value is 0. So L is nothing but x value of the final node minus x value of the initial node divided by the length of the element. And for M, y value of the initial node minus y value of the initial node divided by the length of the element. So the L value and M value we have calculated. We have written down the direction cosines for both L and M. So for element 1 it is 1 and 0, element 2 it is minus 0.707 and plus 0.707. For element 3 it is minus 0.7 plus 0.707 and M value is also plus 0.707. So once the element connectivity data is completed, we can move to write down the stiffness matrix. So the next step is to calculate the stiffness matrix. So for element 1 we have calculated the stiffness matrix from the formula AE divided by L into L square ML minus M L square minus ML, ML M square minus ML minus M square, L square minus ML L square ML minus ML M square ML M square. So once K1, K2 and K3 is calculated for each of the elements, we have to write down the stiffness matrix for this stiffness matrix. Global stiffness matrix is K1 plus K2 plus K3. So K1, direct substitution of the values from the elemental connectivity data, direction cosines. So K1, K2 and K3 is calculated. So while adding the stiffness matrices K1, K2 and K3, we have to observe that node 2 is common in element 1 and element 2. Node 2 is common in both element 1 and element 2. So node 2 is common for both element 1 and element 2. Hence the data pertaining to node 2, which is there in K1, that is 3 and 4, and the data pertaining to node 2 that is there in element 2, that is K2, 3 and 4 are to be added while writing down the global stiffness matrix. Similarly, node 3 is common for both element 2 and element 3. Hence the data pertaining to node 3, that is represented by 5th row and 5th column in element 2 and 6th row 6th column in element 2, is to be added with the 6th row and 6th column of element 3 and 5th row and 5th column of the element 3. Also for element 3 we have a node. Element 3 has one node that is common with the node element 1, that is 1 and 2, row 1 in element 3 and row 2 in element 3, column 1 in element 3 and column 2 in element 3 is to be added with the row 1, column 1, row 2, column 2 of element 1. So here in this particular problem we can see that all the three elements have one or another node common with another element. Hence the addition of the stiffness matrix we have to take care. While adding the stiffness matrix we have to take care. K1 plus K2 plus K3, while adding we have to take care, because there are one node or other node which is common with another element. So once K is calculated, next step is to calculate the global force vector. So from the diagram it is clearly evident that the load is acting only at node number 3 and a downward load of 150 kilonewton is acting. Hence F1, F2, F3, F4 and F5 are 0 and F6 is minus 150 into 10 power 3. Similarly, global displacement vector is Q1, Q2, Q3, Q4, Q5 and Q6. So from the diagram it is clearly evident that the displacement is happening only at node 3. Hence Q1 is 0, Q2 is 0. At node 2 X movement is allowed. Hence Q4 is 0, Q5 will have some value. So by elimination method and applying the boundary conditions, we are eliminating the rows and columns with respect to Q1, Q2 and Q3 and Q1, Q2 and Q4, and Q3, Q5 and Q6 are kept as it is. So there are three unknowns, Q3, Q5 and Q6, and three equations. So solving for this, we get the value of Q3 as 0.2 millimeters, Q5 as 0.1 millimeter and Q6 as minus 0.312 millimeters. So the global stiffness matrix, global nodal displacement vector matrix can be rewritten as 0, 0, 0.2, 0, 0.1 minus 0.312. So next step, direct substitution of formula to calculate the stress in each of the elements. So sigma 1 is equal to E by L into minus L minus M L into L M into Q1, Q2, Q3, Q4. So all the unknowns are calculated, all the unknown values are calculated. So sigma 1 value will be 50 Newton per millimeter square. Similarly, sigma 2 also has to be calculated by the formula E by L2. L2 is the length of element 2 into minus L minus M L M. So L and M pertains to the element 2. L and M are the direction cosines that pertain to element 2. So it is 0.707 minus 0.707 minus 0.707 and 0.707 multiplied by 0.20, 0.1 minus 0.312. So sigma 2 comes to be 53 Newton per millimeter square. Similarly, sigma 3 has to be calculated using the data for element 3 alone. So it comes to minus 53 Newton per millimeter square. Sigma 3 comes to be minus 53 Newton per millimeter square. So stress in each element is calculated. So the next step is to calculate the reaction in the supports, reaction at the supports. So reaction is equal to K into Q minus F. So K matrix is written down multiplied by the Q matrix minus the force matrix F. So when we are directly, this is matrix multiplication and subtraction, we get the reaction forces at node number 2B 75,000 newtons, and at node number R2 is 75,000 newtons, that is at node 1, and R4 is 75,000 newtons at R4 is 75,000 newtons, that is at node number 2. So R5 is 0, R6 is 0. There is no reactions acting at the node number 3. At node number 1 we have 75,000 in the y direction, and at node number 2 also we have 75,000 in the y direction. So with this we have completed this particular problem. We have completed solving this particular problem. So one more problem. This is similar to the previous problem that we have solved. Only difference is the load is 150 kilonewton, which is acting at an angle of 45 degrees. Hence, we have to resolve this load in x-axis and y-axis before we solve it. So the global stiffness matrix, global displacement matrix, the global load the global stiffness matrix and the global displacement matrix remains the same, whereas the global load matrix is different. So for the global load matrix 150 kilonewton, we were directly taking it as minus in the previous problem, but here we have to resolve it in x-axis and y-axis. Hence we are using the sine term and cosine term. So F5 will be cos 45 into 150 kilonewton, and F6 will be minus 150 into 10 power 3 into sine 45. So F6 is the force acting in the y direction, F5 is the force acting in the x direction. So we get the values to be 106,066. So the global force vector, we will write it as, and there is one more 15 kilonewton acting at node number 2. There is one more 15 kilonewton acting at node number 2 in the positive x-axis. Hence F3 will be 15,000. F3 will be 15,000. F3 will be plus 15,000. Hence the load vector is written as F1 is 0, F2 is 0 because there is no load acting at node 1. At node number 2 we have 15,000 newtons acting in positive x-axis, Fy is 0. At node number 3 we have 150 kilonewton cos 45 minus 150 kilonewton into cos 45, that is acting in the x-axis, and minus 150 kilonewton into sin 45 acting in the vertically downwards direction, that is the y-axis. So rest of the procedure remains the same. We are substituting only the load vector. Rest everything remains the same, similar to the previous problem. So we are substituting the load vector and calculating the values for Q1, calculating the values for Q3, Q6 and Q5. So Q3 value we get has 0.04 millimeters, Q6 minus 0.17 millimeters, and Q5 minus 0.13 millimeters. So calculating the values of sigma 1, sigma 2 and sigma 3, that is the stress values in each of the elements. So sigma 1 comes to be 10 Newton per millimeter square, sigma 2 comes to be 0, and sigma 3 comes to be minus 75 Newton per millimeter square. So it is direct substitution of the values AE by L into LM LM sigma 1 is E by L1 into minus L minus M LM Q1 Q2 Q3 Q4. Similarly sigma 2 is also E by L2 into minus L minus M LM. So substituting and calculating the values of sigma 1, sigma 2 and sigma 3. So sigma 1 comes to be 10 Newton per millimeter square, sigma 2 comes to be 0, and sigma 3 comes to be minus 75 Newton per millimeter square. So with this we have solved the sample problems for truss elements and sample problems for bar elements in module